Hello, my name is Paul Lee.
Hi, my name is Derek Lau.
Hi, my name is Stephen Mo.
I'm Jimmy Huynh, and this is our assistive medical walk. The motivation and purpose of this project was to design and construct a device that could help people who often have trouble getting up from a sitting position and getting down from a standing position. This is why we came up with the assisting medical walker, which aids this problem. The walker functions by having a platform that sits on top of the 4-bar mechanisms and acts as a support to distribute the weight on. Once an individual has positioned themselves on the walker, they may press the force sensor to activate a linear actuator to move the 4-bar linkages towards and backwards. As the linkages move forward, it assists the individual from a sitting position into a standing position. And as the linkages move backwards, it assists the individual into a sitting position.
For the kinematic analysis, the initial position of the 4-bar mechanism was 45 degrees. The 45 degrees was made to help a person who was sitting down. From that initial position, the 4-bar mechanism would lift them up vertically to a 90-degree angle to help them stand up. In regards to the velocity analysis, the goal was to be able to reach the final position of 90 degrees within a time span of 5 seconds. To achieve this, the angular velocity was determined to be 0.157 radians per second.
For geometric design of the assistive walker, we wanted to work with a prototype scale based on a scale 1 to 3. The main concern for sizing of components was focused on the forward linkage that will work between starting and end positions. The length of the links were selected based on the previous kinematic design to be 5, 7, and 11.52 inches. Based on that, we constructed the structure of the walker where the forward linkage was going to be attached to. This will resemble the medical walker. The materials needed to make the walker were selected based on the price and the access to machine shop. This is the list of components we used for the project. Because of timing constraints, I'm going to mention the most important ones. For example, PVC pipes were used for the structure. The links were made of acrylic, elbow pads, 2.5-inch screws. This is the final 3D design for the project that contains all the parts from our bill of materials. This image shows the starting position of the walker. This image shows the ending position.
The forces calculated for the mechanism were at the pin joints for each of the links. The external forces acting on the mechanism are the weight of the person, gravity, and the linear actuator. The forces were all calculated using the 3 equations of equilibrium for each individual link. The weight of the person used as a reference was 50 pounds. From our calculations, the highest value of force was determined to be roughly 18 pounds on the pin of the top link.
For stress analysis, the team assumed that the most significant points for stress analysis were the tear-out stress at the connections between the top acrylic link and the bolts, and the buckling stress on the supporting acrylic links when they are in their final position at 90 degrees. The acrylic material had a maximum shear stress of 3,265 pounds per square inch. Therefore, for the safety factor regarding tear-out failure, the team calculated a value of 54.606. As for buckling failure, a critical load of 114.07 pounds was calculated for the 5-inch acrylic link, and a critical load of 58.103 pounds was calculated for the 7-inch acrylic link. As a result, the team calculated a safety factor value of 4.56 for the 5-inch link and 2.32 for the 7-inch link. The team originally believed that tear-out failure would be a more significant issue than failure due to buckling. But according to our safety factor calculations, it seems buckling of the 7-inch acrylic link is most likely going to occur first before any other component.